Welcome to the solar thermal training. This training will focus on technology that use solar energy to produce heat. There are several applications that use heat from solar energy. This training will be therefore structured by presenting the main application that use heat from solar energy. After some generalities about solar thermal energy systems, I will present some water-air heating application, then power generation application. I will also talk about solar dryers and finally about building applications. So let's start with some generalities about solar thermal energy systems. Basically, solar thermal energy systems are transforming solar radiation into heat to be used for its heat-needed application. The major component of any solar thermal system is the solar collector. It is a device that absorbs the incoming solar radiation, converts it into heat, and transfers the heat to a fluid, usually air, water, or oil, flowing through the collector. The solar energy collected is carried from the circulating fluid either directly to the hot water or space conditioning equipment, or through heat exchanger to generate electricity, or to a thermal energy storage tank, from which it can be drawn for use at night or on cloudy days. There are different ways to distinguish solar collectors. It can be on the type of heat transfer fluid, for example, or whether they are covered or uncovered. But the most common way is to distinguish two main categories: non-concentrating stationary and sun-tracking concentrating. A non-concentrating collector has the same area for intercepting and absorbing solar radiation, whereas a concentrating solar collector usually has a concave reflecting surface to intercept and focus the sunbeam's radiation to a smaller receiving area, thereby increasing the radiation flux. Sun-tracking concentrating collectors are suitable for high-temperature applications. To go a bit further in this categorization, here is an exhaustive classification on the existing solar collectors. As previously said, they are separated from non-tracking to tracking ones. Then within the tracking solar collectors, we distinguish those who follow the sun on one axis of tracking from those that are tracking it on two axes. But before describing most of them and giving precision on the purpose that they are used for, here is some technical details for each of them, where absorber type is specified, for example, and more importantly, where we can see the concentration ratio for each technology defined as the aperture area over the absorber area and an indication of their temperature range. Globally, we can see that solar collectors covering a large range of temperature and that more efficient is the tracking, higher is the concentration ratio of the optical device, and higher is the level of temperature reach. So let's start now with the most common application of solar thermal systems, the water-air heating application. It will cover the non-tracking system with the three first solar collectors. For this application, as most of the solar collectors used as non-tracking, they are therefore stationary. They are permanently fixed in position and do not track the sun. Three main types of collectors fall into this category: flat plate collector, evacuated tube collector, and compound parabolic collector. A typical flat plate solar collector is composed of a black-net absorber surface of high absorptivity, where a large portion of solar radiation will be absorbed by the plate and transferred to the transport medium in the fluid tubes to be carried away from storage or use. The liquid tube can be welded on the absorbing plate, or they can be an integral part of the plate. The liquid tubes are connected at both ends by large diameter header tubes, so-called manifold. Many geometrical arrangements for the fluid tubes are possible, but the header and riser collector is the typical design for flat plate collectors. The underside of the absorber plate and the two sides are well insulated to reduce conduction losses. The transparent cover is used to reduce convection losses from the absorber plate through the restraint of the stagnant air layers between the absorber plate and the glass. It also reduces radiation losses from the collector because the glass is transparent to the shortwave radiation received by the sun, but is nearly opaque to long-wave thermal radiation emitted by the absorber plate, which is the well-known greenhouse effect. The advantage of flat plate collectors are that they are inexpensive to manufacture, they collect both beam and diffuse radiation, and they are permanently fixed in position, so no tracking of the sun is required. The collectors should be oriented directly toward the equator, facing south in the northern hemisphere, or north in the southern hemisphere. The optimum tilt angle of the collectors is equal to the latitude of the location, with angle variation of more or less 10 degrees or 15 degrees depending on the application. For example, if the application is hot water production, the optimum tilt is latitude plus 5 degrees to have relatively better performance during winter time when hot water is mostly required. Evacuated tube collectors consist of a heat pipes inside a vacuum-sealed tube that use liquid vapor fast-change material in an evaporating condensing cycle to transfer heat from the absorbed solar radiation to a circulating fluid at high efficiency. The absorber with cylindrical as on the left picture or flat shape as on the right picture, placed in the vacuum envelope, collect solar radiation and evaporate the fast-change material in its liquid state. The vapor of the PCM then travels to the upper part of the heat pipe in the sink region, where it condenses and releases its latent heat to a fluid circulating in the manifold. The condensed fluid returns to the solar collector and the process is repeated. Therefore, several evacuated tube collectors can be connected to the same manifold to compose a whole module. Another possibility is to connect these evacuated tube collectors directly to a hot water storage tank. The reduction of convection and conduction losses due to the vacuum envelope result in better performance and in operating at higher temperature than flat plate collectors. They also collect both direct and diffuse radiation, but their efficiency is higher at low incident angles, which give them an advantage over flat plate collectors in terms of day-long performance. Here are some examples of evacuated tube collectors module integrated to the roof on the left, several modules connected together in the middle, or evacuated tube collectors connected directly to a hot water storage tank for hot water application on the right. Compound parabolic collectors are part of the non-tracking solar collectors category. They are then stationary systems, but they are nevertheless a concentrated solar collectors, which can be seen as an exception from the two main categories described before. They have the capability of reflecting to the absorber all of the incident radiation within wide limits. The necessity of moving the concentrator to accommodate the changing solar orientation can be reduced by using a trough with two sections of parabola facing each other. Compound parabolic collectors can accept incoming radiation over a relatively wide range of angles. By using multiple internal reflection, any radiation entering the aperture within the collector acceptance angle finds its ways to the absorber surface located at the bottom of the collector. The absorber can take a variety of configuration. It can be flat, bifacial, wedge, or cylindrical, as shown in the diagram on the right. It can be manufactured either as one unit with one opening and one receiver, as you can see on the right, or as a panel, as you can see on the left. Let's move now on the power generation application. It will concern the tracking system, where we will focus on 4 solar collectors, 2 with 1-axis tracking and 2 with 2-axis tracking. Power generation is usually made through a process where thermal energy from a heat source is converted into mechanical energy with a turbine and then converted again into electricity with an alternator. This process commonly uses a thermodynamic cycle that runs the turbine between a gap of temperature. More important is the gap, more efficient is the turbine, and more important is the production of electricity. This thermodynamic cycle makes circulating a working fluid, mostly steam, that brings heat from the source to the turbine before being released to the cold source. The heat from the source is transferred to the working fluid with the heat transfer fluid and is released to the cold source with the cooling fluid. Several heat sources can be used in a power generation process. Some of them are from fossil resources like coal, gas, or nuclear, and some others are from renewable resources like biomass or, of course, the sun. About the cold source, water or the ambient air is generally used. For power generation processes that convert solar energy into electricity, the amount of heat collected from the sun needs to reach a high level to run steam turbines far above those attainable by flat plate collectors. Thus, an optical device is used to concentrate solar radiation and reach much higher temperature. High temperature can be reached if a large amount of solar radiation is concentrated on a relatively small collection area. This is done by interposing an optical device between the source of solar radiation and the absorbing surface. In concentrating collectors, solar energy is optically concentrated before being transferred into heat. Concentration can be obtained by reflection or refraction of solar radiation by the use of mirror or lenses. The reflected or refracted light is concentrated in a focal zone, thus increasing the energy flux in the receiving target. We focus here only on the 4 main concentrating collectors that are mostly used in power generation processes. They are presented here in this table in function of its absorber type, whether if it's fixed or mobile, with a line or a point focus, and whether if it strikes the sun on 1 or 2 axes. So let's describe each of them and going a bit further on the technical details of these concentrating solar collectors that are parabolic trough collectors, linear Fresnel reflectors, parabolic dish reflectors, heliostat field collectors. The first of them is the parabolic trough collector. It consists of parabolic shaped mirrors putting in a line that concentrates the solar radiation into a line tube absorber placed along the focal line of the collector and where a fluid is absorbing the heat to be used. This one-axis tracking solar collector is the most advanced of solar concentrating technologies and is the most mature because of considerable experience with the system and the development of small commercial industry to produce and market these systems. Parabolic trough collectors are built-in modules that are then connected together in order to form a solar field of collectors. These collectors can be oriented in an east-west direction, tracking the sun from north to south, which is enhancing the collector performance during the middle of the day as during winter, or in a north-south direction, tracking the sun from east to west, which is enhancing performance during the early and late hours of the days as during summer. The east-west field provides a more constant annual output, but over the year a north-south field usually collects more energy than an east-west one. Therefore, the choice of orientation usually depends on the application and whether more energy is needed during summer or winter. Here are some examples of CSP plants using parabolic trough collectors, with on the right several solar field modules of the emblematic Solar Electric Generating System, so-called SEGS, at Mojave Desert in California. About the linear Fresnel collector, it consists of an array of linear mirror stripes that concentrate light onto a linear receiver. From another point of view, it can be seen as a parabolic trough concentrator that have been cut out into flat stripe and then put it closer to the ground. Thus, unlike the parabolic shaped mirror of a parabolic trough, individual flat stripe reflectors are way cheaper to manufacture and have less structural requirements. Nevertheless, the disadvantage of this technology is the shading that can occur between adjacent reflectors that implies a smaller concentration ratio than parabolic trough. Here are some examples of CSP plants using linear Fresnel collectors, with on the left the CSP Fresnel power station Puerto Dorado 2 from Novatec Solar, and on the right a test loop at Sandia National Laboratories at Albuquerque in New Mexico. Heliostaphyl collectors is essentially used in tower CSP plants. It consists of multiple flat mirrors or heliostats of around 50 to 150 square meters each that concentrate incident direct solar radiation onto a central receiver at the top of the tower. The concentrated heat energy absorbed by the receiver is transferred to a circulating fluid, mostly a gas, since it reaches extremely high temperature above 2000 degrees Celsius. The heat is then used to produce steam at high temperature and pressure. Central receivers have several advantages. They collect solar energy optically and transfer it to a single receiver, thus minimizing thermal energy transport requirements. They typically achieve concentration ratios of 300 to 1500 and so are highly efficient both in collecting energy and in converting it to electricity. They are quite large, generally more than 10 megawatts, and thus benefits from economies of scale. Here are some examples of CSP plants using heliostaphyl collectors. With on the left Themis, the first pilot of solar power plant in the world at Targasen in France, and on the right the Crescent Dune solar power plant in the Nevada desert of USA. About the parabolic dish reflector, it consists in a circular parabolic shaped mirror that concentrates the solar radiation on a point focus absorber and tracks the sun in two axes. It is the most efficient of all collectors with the highest concentration ratio. Nevertheless, its operation and its application are quite different from the other collectors presented previously. Indeed, they are much smaller than the other point focus types absorber of the previous heliostaphyl collectors, which implies that they are rather made to be modular. Although they can be assembled in the field, where they can each collect heat from solar radiation with the fluid circulating in the absorber, and then be transported through pipes to a central power conversion system, it raises design issues such as piping layout, pumping requirements, and thermal losses, especially when the fluid temperature can be above 1500 degrees Celsius. Thus, they are more made to be independent and self-sufficient by converting directly heat into electricity, with its receiver unit located at the focal point. It is generally an engine generator based on a Stirling thermodynamic cycle, better known as Stirling engine, where the heat source is concentrated solar radiation instead of crude oil or coal. Here are some examples of single on the left and in the center, and a field on the right of parabolic dish reflectors with a Stirling engine at the focal point.
To summarize, power generation processes that use concentrated solar energy as heat source are based on the same principle than those using other energy resources like coal, gas, or nuclear, especially for the conversion of heat into electricity that is made in the power block. The only difference is that CSP plant needs to deal with the natural fluctuation of the resource, like the day-night cycle or clouds. Thus, a thermal energy storage can be added in these processes to timely decouple the solar energy collection in the solar field from the heat conversion in the power block. This allows for a smooth electricity production, which facilitates its supply to the utility grid. We will now have a look at the solar dryer application that doesn't need any particular solar collectors properly, but which is another way to use solar energy. Generally, drying or dewatering is a simple process of excess water removal from a product to preserve it. Solar energy can be used in this process to dry mainly agricultural products to reduce its moisture content to a level that prevents its deterioration. Solar drying is another very important application of solar energy. Solar dryers mainly use air as medium fluid to transport the excess of moisture in the form of water vapor from the product to the surrounding environment. According to the product, different conditions are requested to dry it in the best suitable way: solar radiation and temperature, relative humidity, airflow rate. That is why several types of solar dryers have been developed. A large number of geometrical configurations can be used for solar dryers, but they can be classified into three main categories. The distributed type, where solar radiation do not reach the product directly, but use a solar air collector to heat and dry the air entering into the opaque drying chamber, then drying the product by passing through the trays, before being evacuated full of water vapor, mostly through a chimney to the outside. Then the integral type, where solar radiation do reach the product directly, which is dried from solar radiation and the circulating heated air at the same time. And the mixed mode type, which is a combination of both. Fans can also be added to solar dryers that will force the air to enter into the drying chamber and will enhance the process of water removal from the product. That is, define them as active solar dryers that use forced convection transfer instead of passive solar dryers which are using no fans and use only the natural convection in the process. Each type of solar dryers are made for specific products and have different advantages and disadvantages. For the distributed type, they are mostly used for some perishable and fruits, because the crabs do not receive direct sunshine, which avoid caramelization, localized heat damage, and keep the vitamin content in the dry product. But they have the disadvantage of having fluctuating temperature of the air leaving these solar air collectors, which make it difficult to maintain constant operating conditions within the drying chamber. They are also relatively elaborate structures requiring more capital investment in equipment, and they have higher running costs for maintenance than integral types. For the integral types, they have the advantage of easy construction from cheap locally available materials and are used commonly to preserve fruits, vegetables, fish, and meat. The disadvantage is the poor air circulation obtained, which results in poor moist air removal and drying at high air temperatures, around 70 to 100 degrees Celsius, which is very high for most products, particularly perishable. For the mixed mode type, it is a combination of the advantage and the disadvantage of the two previous solar dryer types. Here are some examples of an active integral solar dryers on the left and a passive distributed one on the right. We will finish this training by seeing some building application of solar energy. About building application, one of the principal aims of solar energy is to heat the living spaces. There are several ways to do so, which can be split up into three categories. There is heating by direct heat gain, which is the most common way, where sunlight is admitted into the living spaces directly through opening or glazed windows. Then there is heating by indirect heat gain, where sunlight is going into an intermediate system before reaching the living spaces. For this one, we will have a scope on two different techniques, the rooftop collectors and the thermal storage wall. And finally, there is heating by hybrid heat gain, better known as solarium, which is actually a combination of direct and indirect heat gain ways. So let's move a bit further on these technique details. Direct heat gain is a passive heating technique that is the simplest approach and is therefore widely used, especially in cold climates. In this technique, where sunlight is admitted into the living spaces directly through opening or glazed windows, the sunlight hits the walls and floors, which then store and transmit the heat to the indoor environments. The main requirements of a direct gain system are large glazed windows to receive maximum solar radiation and thermal storage mass. During the day, the affected part of the house tends to get very hot, and hence thermal storage mass is provided in the form of bare massive walls or floors to absorb and store heat. This also prevents overheating of the room. The stored heat is released after sunset when it's needed most for space heating. While windows can admit and trap a great deal of solar energy during clear sunny days, they can also lose a great deal of heat during prolonged overcast period and at night. Providing some form of movable insulation can result in a significant increase in overall thermal performance. Suitable overhangs can also be needed in order to let sunlight entering directly into the living spaces and to benefit from heat gain during winter, but also for shading during summer, which coupled with openable windows for ventilation will avoid overheating. Direct gain is the most common, simple, cheap, and effective heating approach. However, it causes large fluctuation in room temperature because of large variation in the input of solar energy to the room. Glare and degradation of building materials due to ultraviolet radiation are some of its disadvantages. The indirect heat gain is an effective method for reducing the fluctuation in the room temperature. Here, the sun's energy is introduced into the room in an indirect fashion by entering an intermediate system before. The first possible system detailed here is a specific rooftop collector called thermosiphon air panel. It is a passive heating system that can be incorporated as part of the roof. It is essentially an absorbing surface with minimum thermal inertia and a glazing over it, thus forming a solar air heater. It absorbs incident solar radiation and heats up the air in the absorber glazing space. The hot air forces itself into the living space through the vents and warms it up. Cooler air takes its place and the cycle is repeated. In summer, when relief from high temperature is required, the system can be modified to act as a ventilation device. In this case, the hot air is not allowed to enter the room. On the other hand, the room air enters the collectors, gets heated up, and is vented out at the top. This creates a low pressure in the room, leading to cooler air being sucked into the room from windows. This process continues throughout the day and is known as induced ventilation. The second possible system detailed here is a thermal storage wall called the Trombe wall. Invented by Mr. Trombe, this passive heating system is composed of a wall made of material with a high heat storage capacity. It has generally its external surface painted in black, and it is placed behind a glazing in order to absorb a maximum of solar radiation that the wall stores as sensible heat. Then two operating modes are possible. The unvented mode slowly migrates into the wall and radiates in the living space throughout the night if properly designed. This mode is more suitable for residence application and moderate climates. And the vented mode, where air in the space between the glazing and the walls gets warmed up and enters the living space through the open upper vents. Cool room air takes its place through the open lower vents, thus establishing a natural circulating pattern that needs no mechanical means. This heating process by convection and radiation is faster and is then more suitable for daytime use like for office and shops as for cold climates. To summarize, the Trombe wall is a technology that implies a time lag to the heat arriving to the living space, from few hours to a day depending on the properties of the wall and its operating mode. Nevertheless, since these two operating modes are used for winter conditions, during summer the heated air in Trombe wall collector space flows out through exhaust vents at the top of the outer glazing, and air from outside enters the space through openings on the cooler side to replace the hot air. It induces a continuous air movement that cools the living space but induces ventilation. The advantages of the Trombe wall is that glare and the problem of ultraviolet degradation of material is eliminated as compared to the direct gain system. The time lag due to the storage wall ensures that heat is available at night when it is needed most. Besides, one is able to provide sufficient storage mass in a relatively small area. However, a storage wall can block views and daylight. It is desirable to provide movable insulation between the glazing and storage wall. Otherwise, the stored heat can be lost to the ambient at very high rate at night due to the difference in temperature between the ambient and the storage wall. Finally, sun spaces are essentially used for passive heating in cold climates. This approach integrates the direct gain and thermal storage concept. Solar radiation emitted directly into the sun space heats up the air, which by convection and conduction through the mass wall reach the living space. A solarium essentially consists of a sun space or a greenhouse constructed on the south side of the building in the northern hemisphere, with a thick mass wall linking the two. The sun space can be used as a sit-out during days, as it allows solar radiation but keeps out the surrounding cool air. At night, it acts like a buffer space. The basic requirements of this type of building are a glazed south-facing collector space attached, yet distinct from the building, thermal storage link between the collector and living space for heat transfer. The location of the sun space depends on the building design and orientation of the sun. The area of contact between the sun space and the living space determines the size of the former. The thermal mass must be located where winter radiation can reach it. Floors, walls, benches, rock bed, or covered pools of water can be used to store heat. Thank you for your attention.